Today, I'm going to present seismic resilience modeling of Salt Lake County. In this work, I'm collaborating with Chris and Professor John van der Lindt. So to start, to show you Salt Lake County, this is the map of Utah, and this red area is Salt Lake County. And in this picture, you can see Salt Lake City. This is the downtown area of Salt Lake City. This area, this county is the most populous county of Utah. The population is about 1,185,000 people based on 2020 US Census data. And then we have a shapefile for Salt Lake City buildings, which includes 284,000 buildings constructed with 34 archetypes that I'm going to discuss later. And in this work, we are interested on seismic hazard and seismic risk imposed on Salt Lake. And here you can see the shape map that we have for buildings in Salt Lake. To better understand the seismic risk in Salt Lake, here I have two pictures. In the left side, you can see active basin and range province to the west of Utah. And in the right side, you can see the more stable Rocky Mountains and Colorado Plateau to the east of Utah. This area highlighted in orange is called Intermountain Seismic Belt, which is a seismic active region. And since 1847, Utah has experienced 16 damaging earthquakes with magnitude greater than 5.5. In this region, we have a Wasatch Fault that extends from southern part of southern Idaho all the way to central Utah. It's about 240 miles. Wasatch Fault is a normal fault, which means that if we have two blocks, the block above basically drops down during an earthquake. And then here are a few pictures that shows the valley of Utah that experience dropping down relative to the mountain side. And this drop can be in the order of 5 to 10 feet. And in terms of length, it could be around 20 to 50 miles. And this can cause significant damage to physical infrastructure. Wasatch Fault has 10 segments. As you can see, these are the 10 segments of the Wasatch Fault. This red line that you can see shows the fault line. And then from this 10, these 5 segments, including Brigham, Weber, Salt Lake, Provo, and Nephi, are major segments of this fault that can generate large earthquakes. And then, as you can see, Salt Lake County or Salt Lake City is located in Salt Lake City segment and can experience major earthquakes. Recent new fault maps that have been developed for Utah shows that there are seismic active regions that has been not studied previously. And these unexpected areas basically shows that the fault lines are, as you can see in this plot, for different segments of Wasatch Fault. It has been studied and understood that for example, for Salt Lake, it was the fault line was about 57 miles based on previous maps, but based on the new maps, we see that the lines are longer compared to previous maps. And this fault, the Wasatch Fault has the capability to produce earthquakes in the order of 7.6 magnitude, which can cause significant damage to various infrastructure, including buildings, transportation systems, and can cause economic loss in the order of $30 to $70 billion, which is a major loss for Utah economy. And this is why we are interested to understand what could be the impacts of a major earthquake in the order of 7.6 magnitude in the area of Salt Lake County. To do seismic resilience modeling, first we start with community data in terms of built environments, social systems, and economic systems. Our next step is to understand the hazard impacts in terms of the intensity and frequency of hazard. And then once we have this information, the next step is to perform building damage analysis using fragility curves. Then if we have the infrastructure data, we are going to include infrastructure models in terms of water distribution, electric power systems. This is in progress. We are interested to obtain this data and add utility network models to the system, to the in-core model. But so far, we only have building shapefiles. And once we have this information, and once we have the damage analysis results, then we perform functionality analysis and perform functionality state of individual buildings. And finally, we are going to work with social and economic scientists to estimate social and economic metrics in terms of physical metrics, economic metrics, and social metrics. So in terms of Salt Lake County building inventory data, this plot shows the distribution of construction material for buildings in Salt Lake. You can see the distribution of buildings in terms of concrete, masonry, mobile homes, steel, and wood. And in the right side, you can see about 59.1% of buildings are masonry and 38.2% of buildings are wood. Basically, more than 90% of buildings in Salt Lake consist of masonry and wood. To perform earthquake hazard modeling in terms of shake, we performed model-based earthquake modeling using attenuation models available in INCORE. In this work, we are using Cheo and Young's 2014 model from NGA to generate magnitude 7.2 scenario earthquake in the epicenter of 2020 Salt Lake City earthquake. So in this plot, you can see the epicenter of 2020 Salt Lake City that occurred recently, and had and some of the bridges and buildings in the area experienced damages. So we are interested to understand if this earthquake had magnitude 7.2, what's going to be the distribution of damages in Salt Lake. And in the right side, you can see the PGA distribution that we obtained from our simulation. Also, in terms of liquefaction, liquefaction due to strong earthquakes can occur and can cause significant damage to building and physical infrastructure. And in Salt Lake County, liquefaction is a main concern because most of the populated areas lie on Salt Lake sediments. And as you can see in the left side, you can see this is the liquefaction susceptibility map. This area consists of high susceptibility area, and you can see we have different areas with low, very low, and moderate susceptibility. And in the right side, we combine the data that we have from liquefaction maps with our building inventory data, and we obtain this building inventory data with added liquefaction susceptibility column. And then we shared this data with NCSA and uploaded this data to INCORE. The next step is to perform damage analysis and to cluster building damage analysis results. Tu and I worked on mapping occupancy classes that we had from Salt Lake City inventory data. As you can see, this column shows occupancy classes based on the occupancy classes available from HAZUS. And then we developed this mapping between occupancy classes and building clusters to be able to use these building clusters to report damage analysis results. I'm going to switch to Jupyter Notebook for Salt Lake to demo the code that we have developed in collaboration with Chris. So in terms of background, I went through some basic and introductory information on Salt Lake and its Wasatch Fault. So this area shows Salt Lake City or Salt Lake County. We have differences. The first says is prerequisites in terms of modules that we are using, PineCore, PineCore Viz, and Matplotlib and their version. These are three main data sets that we used for our analysis in terms of building data, hazard data, and also mapping, which all are available on INCORE. This cell, as you are all familiar with, we import different packages for the purpose of our analysis, including PineCore and its modules. These are the main steps that we use to perform building damage analysis. It starts with importing INCORE client and services. Then we import building data. We specify hazard and fragilities for the purpose of our analysis. Then we set up and run damage analysis without liquefaction, plot results, and summarize the analysis data for each one of the clusters that I showed you in the PowerPoint. And then we plot liquefaction susceptibility map. Also, we set up and run damage analysis with liquefaction to understand what's going to be the impact of incorporating liquefaction impacts on our damage analysis, and we report damage cluster with liquefaction. So this cell shows that we import in-core client and data service. Once we have these two clients, the next step is to import building data in terms of building data set. This is the ID that we used, and this is going to be shared with you. So if you are interested, you can take a look. And then we import data set using in-core modules. The next step is to specify hazard and fragilities. As you know, we are interested in seismic impact, so hazard type is earthquake. This is the hazard ID based on NGA West model that we use to create the earthquake with magnitude 7.2. And also, this is the ID that we use for liquefaction data set. In this study, we were interested to also account for damages to mobile homes. So we created a new mapping based on the mapping that we had from Shelby County. So this is the ID that we are using for Salt Lake City to map fragility functions to individual building structures in Salt Lake City. Then we set up and run damage analysis without liquefaction. This is the result name, Salt Lake City damage, building damage without liquefaction. So these are two input data sets in terms of buildings and also mapping sets. And also we set parameters in terms of result name, hazard IT, and number of CPUs. And then we run building damage analysis. Then the next step is to obtain the outputs from damage analysis. So as you can see, this table shows probability of exceeding different damage states, including insignificant, moderate, extensive, and complete damage states for different buildings. Here are 5 example GUID buildings. Once we have this information in this cell, we also add structural system type and also structural system type and geometry data for the purpose of plotting. In this cell, we did some statistics on probability of being in damage state number 3. So you can see the number of buildings in damage state 3, mean, standard deviation, and other statistics. And this plot shows the complete damage value and the number of buildings that experience damage state number 3. And this map shows the distribution of damage state number 3 probabilities, as you can see. And this case is without liquefaction, as I mentioned earlier. In this cell, we did some Python coding in order to map buildings to clusters. So you can see these are the clusters that we are interested to report our analysis results. For example, for critical medical, you can see 39 buildings are in significant damage state, 277 moderate damage, and then 143 extensive. And you can see all the other cases and different damage states. I had this plot on my slides, but using in-core, we import the data, the liquefaction susceptibility data based on the dataset ID, and then we plot the susceptibility probability for different regions of Salt Lake. And now we want to set up and run damage analysis with liquefaction. One main change that we need to make is this line, that we set parameter use liquefaction to be true in order to account for the impacts of liquefaction. And then we need to specify the liquefaction data set for the purpose of analysis. And all the other parts of the building damage analysis gonna stay the same. Then we run our analysis, and again, we report cluster statistics in terms of number of buildings that experience different levels of damage states. So I'm going to go back to the slide, and these two tables compares the data that we obtained from our analysis in terms of number of buildings for different clusters that experience different levels of damage states. For example, if we compare critical medical data, you see for the case without liquefaction, 277 buildings are in the state of moderate. And then when we account for with liquefaction, this number goes down to 232. And then extensive, you can see that when we account for liquefaction, we have more number of buildings that experience extensive damage level. And then you can compare all other cases to understand what's going to be the impacts of accounting for the impacts of liquefaction in seismic damage analysis. Also, in this cell, Chris included some codes to see how we can have access to liquefaction data in a specific location, so we can define demand units and location that we are interested in, and using hazard service module of INCOR, we can obtain the information that we are interested in terms of liquefaction data. So far I discussed damage analysis with and without liquefaction. The next step gonna be functionality analysis. So we previously did some analysis in terms of functionality analysis, and we only consider shake only because on that time we didn't have the liquefaction code that Chris recently provided to us. I just wanted to show you the results that we obtained from our previous analysis, but we are going to update our analysis in order to account for liquefaction impacts as well. So we worked with economic team, and then we identified 9 PUMA regions. And recently, the econ team decided to reduce number of PUMA regions to 7 different areas. But in this analysis, we started with 9 PUMA regions. So for different PUMA regions, we were interested to see how many buildings would be functional in each one of these PUMA regions, and what's going to be the impacts of physical damage in terms of economy. And in this slide, you can see 3 example PUMA regions. And as you can see in each one of these plots, you can see number of buildings that they are functional or non-functional. For example, for PUMA region 7, the analysis shows 92% of buildings would be functional and 7% of buildings in this PUMA region would be non-functional. We can obtain similar results for other PUMA regions as well. And this table summarizes the number of functional building estimates for different PUMA regions. So you can see the number of functional buildings, number of buildings, and percent functional for different PUMA regions. And in terms of the next steps, we would like to incorporate utility infrastructure model to the model that we have developed for Salt Lake so far. We are going to work with social and economic scientists, including Nathaniel, to do population dislocation analysis. He has completed housing unit allocation data, and the data is available for us. So the next step is going to be to do population dislocation analysis. And also we are going to continue our collaboration with Harvey and his team to perform economic analysis. And also we are working with Zhang and NCSA to implement Salt Lake CTR. So this is the end of my presentation. If you have any questions, please let me know.